All right, so this video is going to cover examples of finding inflection points. And again, we're in section 3.4. Now, finding the inflection points, the way we do it's going to be pretty much exactly the same steps as when you're finding intervals of concavity. So it's going to be all the same stuff, or same steps as finding the intervals of concavity. It's just going to have an added step or two in which you determine the point in which it switches from concave up to concave down, or vice versa. That point is going to be an inflection point. And so that's the added step. We determine whether it's an inflection point when it switches concavity, and then you would find the y coordinate value of that inflection point. So I wrote up the strategy, and you'll see it's very similar or identical to the strategy from the previous video when we dealt with intervals of concavity. So the strategy goes, the first step, we're going to find the first and second derivatives. So that's f prime of x and f double prime of x. Second step is to find any potential inflection points. So I'm just calling it potential inflection points by setting the second derivative equal to 0. Or seeing where its derivative, second derivative, doesn't exist. I would say probably 99% of the time, we're just going to be dealing with when the second derivative is equal to 0. The third step is going to be forming the intervals. So you find your potential inflection points. Based on those inflection points, you're going to form the intervals, and you're going to pick a test value from each interval. And the fourth step, this is we're going to determine which interval is concave up or concave down. And that you do that by plugging the test values into the second derivative and make note of the sign. So if the second derivative is positive or greater than 0, then it's concave up. Second derivative is negative or less than 0, then it's concave down. And then the third one, if the second derivative equals 0, then the function itself is linear. This fifth step was the added step. So all these first four steps were the same from the previous video for finding intervals of concavity. It's the fifth step that's just an added step where we're going to see which point is an inflection point out of the potential inflection points. And so that's just, does it switch concavity from concave up to concave down, or concave down to concave up? If so, then that's going to be an inflection point. And then you're going to find the y coordinate of that inflection point by using the original function. All right, so that's the strategy. If you want to pause the video and write that down, I recommend doing that. And now I'm going to invoke the strategy for these two examples. All right, so number 17. All right, so our goal here, is to determine the inflection points. And I'm just abbreviating it IP. All right, and we need to first determine the intervals of concavity. So we're going to find intervals of concavity first, because you need to know where it switches concavity. All right, so that's what we're going to do. We're going to find the inflection points, and in the process of doing that, we're going to find the intervals of concavity. And this was done in the previous video. All right, so first we need to find the first and second derivatives. Now our function's x cubed minus 9x squared plus 24x minus 18. to the first derivative, f prime of x, so we use the power rule, x cubed becomes 3x squared, right? Because it's 3x to the 3 minus 1, so that's 3x squared. And then the derivative of 9x squared, so we're going to have minus 9 times the derivative of x squared. Power rule for that, that's 2x. And then 24x, the derivative of x is 1, so that's going to be plus 24 times 1. And then negative 18 is a constant, so its derivative is 0. All right, so I'm just going to write it over again. So f prime of x, it's going to be 3x squared minus 18x plus 24. All right, so that's the first derivative. Now we got to find the derivative of the first derivative. So we got to find the second derivative. That's f double prime of x. So let me use a different color for the second derivative. I'll use yellow. So f double prime of x, that's going to equal, and we take the derivative of 3x squared. That's going to be 3 times 2x, because the derivative of x squared is 2x. And then 18 times x, that derivative becomes minus 18 times 1. And 24 is a constant, so that's derivative is 0. So 6x minus 18 is the second derivative. All right, so I'll circle that because we'll be using that for when we plug in our test values. All right, now we're going to find potential inflection points. All right, so either the second derivative doesn't exist or it's going to be equal to 0. There's no x values for which the second derivative doesn't exist because 6x minus 18 is a polynomial. All right, so we only focus on when its derivative, second derivative is 0. So we're going to find x so that f double prime of x equals 0. All right, so we set 6x minus 18 equal to 0. All right, so we solve for x, we add 18 to both sides, we have 6x equal to 18. And then divide by 3. So 18 divide by 6, that gives you 3. All right, so 18 divided by 6 is 3. All right, so that's our potential inflection point. And I usually just call it x star. And then that's equal to 3. So that's my potential inflection point. I'm going to circle that. So that's what we needed to determine. Now I need to find intervals of concavity. So our intervals, let's say I have a number line, and here I have 3. So I have the values that are to the right of, or sorry, to the left of 3 and to the right of 3. So everything that's to the left of 3, that's negative infinity to 3. And then everything to the right of 3, that's going to be 3 to positive infinity. So I pick a test value from each one, and for the test values, I'll pick 0 from the first one because 0 is an easy value to plug in. So I'll use 0. And then for the second interval, I'll use 4. So my test values are 0 and 4. So what I need to do is I need to plug these into the second derivative and see if it's positive or negative. So now plug into f double prime of x. And the second derivative was 6x minus 18. So I plug each value in. So let's do the first one, 0. So x1, 0. That's going to be 6 times 0 minus 18. And that gives you negative 18. The point is that that's negative. So we only care about the sign. So what does negative mean for the second derivative? That means the graph is opening downward, so it's concave down. And that 0 value came from the first interval, negative infinity to 3. All right, and I'm boxing that in red just because when you do the problem in the textbook, they're going to also ask, in addition to the inflection point, they'll also ask for intervals of concavity. All right, so it's concave down on negative infinity to 3, and hopefully it's going to switch to concave up for the second interval for it to be an inflection point. So the second value is 4. Plugging that in the second derivative, that's 6 times 4 minus 18. All right, so that's going to be 6. And it's positive. So since the second derivative is positive, that means it's going to be concave up. And that came from the second interval, 3 to positive infinity. All right, so these were my intervals of concavity. So from here, I can determine whether 3 is going to be an inflection point because it switches concavity. So our x star equals 3 is an inflection point since it switches concavity. All right, now I just need to determine, well, what's the y coordinate for this inflection point? So last, determine the y coordinate for the inflection point. And it's crucial to be aware of which functions you're using. And for this, we use the original function because we were dealing with the original function's y coordinate. So the original was f of x, and it was equal to x cubed minus 9x squared plus 24x minus 18. That was the original function. All right, so now I plug in 3. All right, so 3 cubed minus 9 times 3 squared plus 24 times 3 minus 18. And if you do that in a calculator, this comes out to be 0. All right, that's the y value, that's the output. And then 3 was the input. So the inflection point is 3, 0. All right, so in conclusion, I mean, we've done the question, but just to summarize, we had the intervals of concavity, it was concave down from -infinity to 3. And then concave up for 3 to positive infinity. And then we had the inflection point being 3, 0. All right, that's just to summarize. All right, so that's pretty much it for that question. Now the next question is a trig function. The next one's number 27. And it's sine, and then I put in parentheses. The textbook doesn't have the parentheses, but I like to put it just to reinforce that the argument of the sine function, in this case, is the whole thing, x over 2. And then they tell you a domain, 0 to 4 pi. All right, so they specify a domain. I will say, just to comment before I work the problem out, is note, you can't have an endpoint be an inflection point. All right, so 0 and 4 pi are not going to be inflection points. So you might work the problem out and you might get potential inflection points. And let's say potential inflection points happen to involve 0 and 4 pi. Well, then you would eliminate those two choices. You can't have the endpoints be an inflection point. All right, so we're going to have to use chain rule because of the inside functions x over 2. Now, it might be beneficial to write it as the following. So sine x over 2 is the same thing as 1/2 times x. Sometimes I like to write it like that, just to, I don't know. And the derivative of sine, if we apply the chain rule, so derivative of sine of u is cosine u times u prime. In this case, u is 1/2 x. So u prime is going to be 1/2 because the derivative of x is 1. All right, it'll be 1/2 times 1, so that's 1/2. So the derivative f prime of x, so the outside function sine, that turns into cosine, and then the same argument, 1/2 x times 1/2, because that's u prime is 1/2. All right, so you could just go ahead and put the 1/2 in front. Okay, so this is the first derivative. Now I need to find the second derivative, and I'll put that in green. One thing to know, derivative of cosine. So we're going to have to do chain rule again, but involving cosine. And the derivative of cosine, that's going to be negative sine of u times u prime. U is a half x again. So that means u prime is going to be 1/2. So because of the 1/2 from the beginning, I'll do f double prime of x, factor out the 1/2 that's already there, and then focus on the derivative of the cosine 1/2 x part. So that's going to be negative sine of u times u prime. So u is 1/2 x. So it's going to be negative sine of 1/2 x times 1/2. That's going to equal 1/2 times negative sine 1/2 x, and then times u prime, which is 1/2. So I just do a half times a half is 1/4, and then there's a negative sign. So the second derivative is going to be negative 1/4 sine of 1/2 x. Okay, so that's the second derivative. And I'll circle that because we're going to be using this for what we plug in for the test values, and also we're about to use it again for the inflection points. So now I'm finding the potential inflection points. So sine is continuous, its derivative exists everywhere because it's and so there's no cases in which the second derivative, in this case, there's no cases in which sine does not exist. So we only worry about when the second derivative equals 0. I'm going to find x where f double prime of x equals 0. All right, so we set negative 1/4 sine of 1/2 x equal to 0. So you could divide both sides by negative 1/4. I guess I'll go ahead and show it. But you can go ahead and divide by negative 1/4. 0 divided by any number is 0, except for 0, but we're not dividing by 0 in this case. So we have sine of 1/2 x equal to 0. So I need to find x where sine of 1/2 x is 0. And the way I do it is I'll treat 1/2 x as theta, and I'll ask myself, find theta where sine of theta is 0. And then I'll back substitute 1/2 x in for theta. The same thing as doing the inverse sine of both sides, but there's multiple values for which sine is 0, right? So on the unit circle, you have sine of 0 at 0, you have pi, 2 pi, and then it keeps going, 3 pi, 4 pi, keeps going like that forever. So you could also have negative pi, negative 2 pi, and so forth, but these are all multiples of pi. So sine of theta equals 0 when theta equals n times pi, or n is an integer. All right, so in this case, now I just substitute, well, 1/2 x in for theta. So sine of 1/2 x equals 0. So when instead of theta equals n times pi, it's going to be 1/2 x equal to n times pi. All right, then to get rid of the 1/2, you multiply both sides by 2. So that's going to be when x equals 2n pi. So even integer multiples of pi. Now keep in mind our domain is 0 to 4 pi. So what I've found now is the general solution for the second derivative equaling 0. So for our domain, okay, so even integer multiples of pi. So that's essentially 0, 2 pi, 4 pi, and those are even integer multiples of pi. But because we can't have an endpoint via inflection point, we don't consider 0 and we don't consider 4 pi. So only 2 pi is our potential inflection point. Okay, and that's, so potential inflection point is 2 pi, and I'll just label it x star. Again, so when I solve these kind of trig functions, I get the trig function by itself, and then I treat whatever the argument, so what's inside, the stuff that you're taking the sign of, I kind of replace that with theta, and I look at the unit circle and see what values on the unit circle is signed to your 0, and that happens when theta is 0, pi, and 2 pi, as you can see on the unit circle, and it's just basically any integer multiple of pi. All right, so that's why I have theta equal to n times pi. All right, and then I just substitute 1/2 x in for theta. So it's going to be, instead of theta equal to n times pi, it's 1/2 x equal to n times pi. And solve for x, so you multiply both sides by 2. That's where I get 2 in pi. And then I look back at our domain, 0 to 4 pi. Even multiples of pi, that's like 2 pi, 4 pi, I guess 0. But we just can't have 0 and 4 pi because those are endpoints. And you can't have an endpoint be an inflection point. So that only gives us 2 pi. So now I'm good to go on and find the concavity, intervals of concavity. So we go from 0 to 4 pi. So we have 0, 4 pi, so 2 pi in between that. And when we form our intervals of concavity, we also don't include the endpoints. We always use open intervals. So always parentheses. So our options are, I have between 0 and 2 pi. And then I have between 2 pi and 4 pi. All right, so I pick a test value from each one of these intervals. And I'll use, let's go orange. So I'll pick pi from that interval, and then I'll pick 3 pi for the other one. So my test values are pi and 3 pi. All right, so I plug these into the second derivative. And then see if it's positive or negative. And the second derivative was negative 1/4 sine of 1/2 x. All right, so the first one's pi. I plug pi in. That's negative 1/4 sine, and it's 1/2 times pi, so that's pi over 2. And what's sine at pi over 2? So sine at pi over 2 is 1. This is negative 1/4 times 1. So negative 1/4, so it's negative. All right, so since it's negative for its second derivative, that means it's concave down. And that came from the interval, or test value came from 0 to 2 pi. Okay, so that's part of the answer as far as intervals of concavity. And hopefully for this second interval, it'll be concave up, so that way it switches concavity. So the second value we picked was 3 pi. That's going to be negative 1/4 sine of 3 pi over 2. Well, sine of 3 pi over 2 is negative 1, so this is negative 1/4 times negative 1. That gives me positive 1/4. So it's positive, so it's concave up. And that came from the second interval, which is 2 pi to 4 pi. All right, so that's my intervals of concavity. So it does switch concavity at our potential inflection point. Or again, our potential inflection point was 2 pi. Right? So we base these intervals off of 2 pi. So since it switches concavity, so our x star equal to 2 pi is in fact an inflection point. Now the last thing we need to do is just find what's the y coordinate that goes with this inflection point. In the original function, we have to always use the original function. So back in the very beginning of the question, the original function is f of x equal to sine x over 2. All right, so we just plug in our inflection point. So for x star equal to 2 pi, that's going to be sine of 2 pi over 2. So sine of pi. And sine of pi is 0. All right, so that's our output is 0. And then the input was 2 pi. So the inflection point is 2 pi comma 0. All right, so just to summarize, we had the concavity, intervals of concavity were 0 to 2 pi, concave down, and then concave up from 2 pi to 4 pi. And then our inflection point was 2 pi comma 0. All right, so that's the answer to this. The next video, I will apply the second derivative test, which is a completely different thing than finding inflection points.